Okay. All right. So what we're going to do today, it is called simple harmonic motion, and it is basically in short form we call it SHM. Okay. Now, so first of all, the most important thing you need to understand is the definition of this, because the first thing in every question they're going to ask you this definition. Okay. So we're going to write, it is a 2-mark definition. So first, for the first mark, we're going to write that, okay, let me just start it this way. It is the to and fro motion of an object, and then for first mark they will say, you say always that the acceleration is always directed towards the mean position. Okay, so this is the first mark, and the second mark is for writing the magnitude of acceleration is directly proportional to the magnitude of displacement. Okay, so you can combine this, if you want to, but I just want to tell you that you need to focus it here. Okay, now so suppose we have a spring which is here. Okay, and this we can call as the mean position. This is mean position. Mean position basically means that at this point there is no acceleration. Okay, now so it can either, when you oscillate it, so it can become smaller like this, it can compress itself, or in another instance it could be bigger than this. Okay, so what I want to tell you is that basically the acceleration is always directed towards the mean position, which means the acceleration will always be towards the mean position, whether this is compressed or it is stretched. So there could be two cases, right? However, in this case you might see that the displacement is x here. If I'm taking this side as positive, then I'm putting negative sign here, but both of them are vector quantities, and in this position the displacement is positive x and acceleration is negative because it is opposite direction. Do you guys understand this?
Yes.
Okay, now what I'm going to claim in front of you is that basically this acceleration is, from the perspective of the definition, it means acceleration's magnitude is directly proportional to the displacement's magnitude. But I'm putting a negative sign. This negative sign, negative, shows they will always be in opposite directions. As you can see that when acceleration is positive, the displacement is negative, and when the displacement is positive, the acceleration is negative. So you just need to remember that. All right, now if I open this up, so I will get a formula which is minus omega square n x, where this is the angular speed squared, right? And this is the displacement, and this is the acceleration. Now this is what I will prove later on, that how this is possible, but for now just remember this is the most important formula that you need to remember. All right, okay, please write this down. Okay, now some math lesson. So some of the calculus we still need to learn in physics, and we're going to do it today. So just try to stick around. Wait a second, please. I'm sure you guys already know this, what I'm going to tell you, and even if you don't want to write it, it's fine, because they won't ask you this directly, but it's always good to remember. Okay, so what are we going to do? We're going to make a function of y, and then we're going to find the derivative. Now derivative in math, those who don't take math, basically means dy dx means that whatever the graph of y and x is, we are going to find the gradient. Okay, and gradient is change in y over change in x. Basically change in y and change in x is the same thing as dy and dx. Yes?
Are you recording?
Yeah, it is recording. It's on YouTube. Okay, all right. And then we would also want to make a set here of dy and dx. This is y, dy and dx. Okay, so this is just a gradient. Now first of all, we're going to look at sine of x. So what it means is that I'm doing y equals to sine of x, like that. Okay, and then the next one is cosine of x, and then I would like to do minus sine of x, and then minus cosine of x. Okay, so remember, when you basically take gradient of the graph of sine x, you will always end up with a cos x graph. Okay, when you take cosine is very mean. So what cosine does is it puts a negative sign and converts itself to sine, like this. And then sine doesn't change the sign, so basically minus sine would mean minus cosine x, and minus cosine would mean plus sine x. So whenever you derivate or you take gradient of cosine x, whatever the sign, negative or positive, is with it, it will convert to the other one. Is it clear, everybody? Now sometimes
Yes, sir.
they will also give you like sine of ax, like this. So basically x is the function where a is a constant or something, right? Or any other variable, doesn't matter. So this will be cos ax, and then we're going to look at cos minus sine ax, and then minus cos ax. Now what you're going to do is, whenever this will come, the constant which is inside is going to multiply outside. So we're going to write a and then convert it to cos and ax. That would be the function, right? Like this. And then cos would be minus a sine of ax. Minus sign would be minus a cos of ax, and cos will change the sign, so plus a sine of ax, like this. So it's pretty simple. You just need to multiply the value or the variable that is next to the function outside and keep the rest the same like the previous one. Okay, now if a function is like, suppose a sine bx, okay, and then it's a cos bx, and it is minus a sine bx and minus a cos bx. So what you're going to do? So you're going to multiply. The same thing doesn't really matter. So you're going to write it as a is already there, b will come outside. So ab cos of bx. This will be minus ab sine of bx. This will be minus ab cos of bx, and then finally change the sign, and then ab sine of bx. Everybody understands this?
Sir, is there like a set way to remember this, or we just by heart? Like we just mark it out?
Like, I have just learned the rule. The rule is that the cos will always change to sine, but cos also changes the negative or positive sign, right? And if there is like a constant or a variable next to the function, I just need to bring it out no matter what. So I just remembered this. But you can also learn this, right? Because you need to understand, because sometimes they're going to give you an equation and then you have to. Who's asking me this?
Yeah, that's fine. Yeah.
Okay.
So can I just copy?
You want to? Yeah, why not? Just copy, take your time. Let me send a link to somebody. I don't. Oh no. Wait a second, please, okay? These people I don't like, you know? Okay. Yeah. Sorry. Yes, go on. Right. Okay, you guys done? Should I move forward?
Good.
Okay. Now, when I'm talking about simple harmonic motion, right, it's very important to understand, and this is something I would like to, show you, that let's suppose they say there is some function, right, or some harmonic motion that has an equation which is of the displacement, right, x equals to x naught. X naught is, say, the maximum displacement. In fact, let me write it down so that you guys are not confused here. So let's suppose they've given an equation, x equals to x naught sine of omega t, right, like that. So, well, let me this is basically the instantaneous displacement. This is the maximum displacement, and the function is sine, and omega, is the angular speed, and this is the time. Alright, so this is the equation given already. You just need to remember that because we've learned that omega was supposed to be theta upon time, so theta and omega t are basically the same thing. That comes from the very first chapter of circular motion. Now let's look at this. Whenever you make a sine curve, so remember, if I'm starting from this point, right, so I'm basically making a circle with it, and let me make a circle because I'm really bad at making circles. I'm going to make one that's given here. Okay, like that. So I'm starting from, this is the center of the circle. I'm starting from this point like this, right? So let's call this A. Let's call this A. So when I moved to basically a 90 degrees, which means that basically in a circle, if I go from here till here, basically I cover a distance of 90 degrees, right? So 90 degree means that after 90 degrees I'm gonna get a displacement like this. Do you guys understand this? A quarter, right? Now from point B, so this is point B, if I go to point C, which is right here, C, so now I have covered another 90 degrees, which makes a total of 180. So when I say 180, it means, as you can see, it has come here, which basically makes it go like this. Oopsie. Told you, I'm bad at this. Okay. Right. Now, so this is C. And then if I go to, say, this point, which is D, so you will see that basically 90 degrees again, so it's 270 degrees, which means that actually now I'm at this displacement. I'm going to continue this line right here, and it will go like this. Is it clear, everybody?
Yes. Yes, sir.
So I'm moving like this, okay? And then when I come back to A after one whole rotation, so that is basically 90 again, that's 360 degrees. So 360 means now you can see I'm back to the 0 point. So basically the displacement will again be 0. So here's displacement. So you see that basically I've made this curve is sine theta curve. Basically any sine theta curve is like a wave, okay? So when you complete one circle, so it will actually depict this. Now, how am I saying that this equation that I have written here is equivalent to the graph above? Okay, so let me just show you this with a different color actually. So what you guys need to understand is that if, let's suppose, I want to go right here, okay, this would mean that I am at a displacement, say this displacement is x, and the top displacement is x naught. That's the maximum you can reach, right? So I'm looking at this displacement right now, which is this. I can also draw it like this. So this would be the displacement. So I can say this is x, and also if I'm saying that this is the total length, the pink line, this one, okay, this is equivalent to x naught. How is it possible? Because you see, if this length, like starting from here, if this length is x naught, and you might see that it also represents the radius of the circle, so basically x naught is the same, this line is also the radius, so these lengths are same, right? Now this makes it a triangle, so this is 90 degrees. And now please look at this. I could say that sine theta is basically opposite over hypotenuse. That's maybe you learned in AS. The opposite of this triangle that I'm looking at is x, and hypotenuse is theta, x naught. So if I multiply x naught there, so x will be equal to x naught sine theta, whereas I know that theta is omega t, so I'm going to replace this. So sine omega t, and hence I get this equation. Do you guys understand this?
Yes, sir.
Now you do not need to worry about this because you just need, they will always give you this equation, but you need to learn how to convert this. That we're going to learn today. Now let's check it out. So for example, so I'm going to give you an example here. Example. Suppose displacement equation is given. Okay, and the equation is like, I'm going to write displacement, and the equation is x equals to x naught sine omega t. And now I want to convert it into velocity equation. So I'm going to give you a little bit of, understanding here. Who's going to tell me what is the definition of velocity? Anybody?
Rate of change of displacement.
Exactly, right? You said rate of change of displacement, which means velocity is just change in displacement over change in time. Basically what you're doing is you're finding change in displacement x over change in time, like that. Okay, so that basically represents velocity. So this means that if I find the gradient of this is going to give me the velocity, right? Now I have the equation, so I'm going to write change in x over change in t would mean, which is velocity. Now I'm going to change this. Look at the function, right? I am changing this x with respect to this t. Can you tell me what will happen now? I just showed you through the tables. So I'm going to write sine changes to cos, right? And omega comes out. So can I write it as x naught, omega comes out, and then change it to cos omega t. Can I write this?
So could you repeat that?
Yes, again. So we have the equation for displacement right here, you see? And according to our definition, velocity is, let me write it like this, change in displacement over change in time. Now, if I want to find the velocity, I need to take the gradient of this equation. Do you guys agree? So my equation was x equals to x naught sine of omega t. If I want to find dx, change in x over change in time, what will I do? I will multiply this outside, so omega x naught, can I write it like this? Convert this function to cos, and then keep the rest of the things same. Exactly what we did here, you see, when you convert this one, you see? Now check this out, and let me know if you don't understand this. So this would be the equation of velocity. Everybody understands this?
Yes, sir.
Now, let me write it nicely. So basically we've got a new equation of velocity, which is v equals to omega x naught cos of omega t. So let's keep it there. Now, who's going to tell me the definition of acceleration?
Rate of change of velocity.
Rate of change of velocity, which means that basically acceleration is the change in velocity over the change in time, right? So basically what we're doing is we are finding the rate of change of velocity by doing, we're going to take the derivative of this, right? Or I say gradient. Now, what is our equation? Our equation is v equals to omega x naught cos of omega t. So who's going to tell me if I want to find dv by dt, cos changes to what?
Negative sign.
Negative sign. Cos changes to negative sign, and this omega will also come out again. So what I'm going to get? Minus omega square x naught, which is all, this is already there, so omega comes out and multiplies with omega again, and sine of omega t. Do you guys understand this?
Yes.
Okay, so now the equation of A is minus omega square x naught sine of omega t. Acha. Now see, you might be wondering how difficult it is. It is not really difficult once you get to know the rules, right? To change it, because they can give you any cos or sine equation of any of these, and you just need to follow this rule. Remember, you have displacement, you have velocity, and you have acceleration. So these are the three things you're gonna change. So when you go from displacement to velocity, you have to take the derivative of that equation. So dx, second please, dx by dt, and when you go from velocity to acceleration, you need to take the derivative of dv by dt. You're gonna end up like this. So you just remember this small thing and you change it. Now, all this effort has to be done because I have to prove something, right? So what? Yes.
Over there you wrote displacement to velocity to acceleration. Can it be the other way around in the question?
No, it can't go like for other people. Just to give you an extra knowledge, right? If you go from acceleration to velocity, you need to find the integral, and integrals are not in physics. Okay, so chill. Okay, so that's not there, only derivatives. Now, so displacement we wrote, and then we're going to write the equation of velocity, and then we're going to write the equation of acceleration, and then I'm going to do a magic trick, right? And you might, there is always a show-stopping move. So this is my show-stopping move. So what we just learned from the previous example was that, continuing with this, x equals to x naught sine omega t was this equation. Its equation was v equals to omega x naught cos omega t, and acceleration was omega squared x naught sine omega t. Now you might see something very important here. If you look at it, this whole thing and only this section is the same. You see? Sorry, there is a minus sign as well. Yes. If I replace this right here, what I'm gonna get? I'm gonna get acceleration to be minus omega squared, and instead of all of this, what I can write it is as x. Did you see this equation before? So this equation is basically the same one that I claimed in the first part, that this is the equation of SHM, and through that example we have proved that yes, the acceleration is basically the magnitude of acceleration is directly proportional to displacement, and they're always in the opposite direction to each other, or you could say acceleration is towards the mean position. Everybody understands now? If you have any questions, please let me know. Acha, I just want to tell you that in 6 minutes the meeting is going to end. Okay, so I'm gonna send you a new link. Well, it doesn't really matter because my link is static, so you can just click the same old link, you will join it. So I have to just refresh the meeting. Okay, now let's go forward.
So can you actually scroll up just a bit?
Yes, here.
Yeah, just the acceleration.
Okay. So you guys might have, do you guys know about pendulums? Or no? Nobody knows about pendulums? Okay. Fatma, this is your first class? Fatma, you need to join Google Classroom actually. Okay?
Okay.
Okay. The link to Google Classroom. Please don't leave the meeting at the end, okay? because I want to add you there so that you can access the previous things. Okay. All right, now let's go forward. Okay, it's almost 3 minutes, which is great. Okay. Now we can also make the graphs of it, and the graphs are very important because they will help you understand what we're actually achieving here. Okay, right. Give me like 2 minutes, please. 1, 2, 3, 1, 2, 3, 4. Okay. Okay, please. All right. So, say this is displacement and time graph. This is velocity and time graph, and this is acceleration and time graph. Right. So we're going to follow the same way. We're going to say, okay, the equation of x displacement was x naught sine omega t, and remember this is not a fixed equation, right? I mean the pattern remains the same, but it could be cos or sine, depends on the question itself. But we're following that example. So which means if I make a graph of this, so sine graph is always like this. Remember that. Like this. Okay. Which means that here this point is our x naught. Remember this. Now, and this point is minus x naught. Now, the equation for velocity was v omega x naught cos of omega t. So this will be a cos graph. So which means that this is going to be something like so when it is 0, the velocity is going to be maximum. When it is maximum, the velocity is going to be 0. So it's going to go like this. And then when it is 0, 0 again, the velocity is going to be maximum. Like this. And then when it is maximum, velocity is going to be 0. And then when it is 0, velocity is going to be maximum again. Maximum again, like this. Okay, so you might see that this basically it makes a cos graph, and I'll explain why it is like this and how did I know that when it is 0 and when it is maximum. Finally, for acceleration, when it is 0, acceleration is also 0. When this is positive, the acceleration has to be maximum, but in the opposite direction, which is negative. And then when this is like 0, so acceleration has to be 0 again. When it is maximum in the opposite direction, it has to be like this. And yeah, this would be something like this. Okay, now let me explain this thing. So okay. Okay, wait a second. Let me post it there. Okay. All right. Here we go. Okay, Gatika, Suha. All right, let's just uh, just one more minute, okay? Let everybody join back. Interesting. Now, okay, so the acceleration's equation was a equals to minus omega square x naught sine of omega t. Now let's check this out. So remember, yes. Yes. Okay, now see this. Let's take an example of a pendulum, right? So when you're looking at a pendulum, so this is its equilibrium position, and the two maximum positions could be either here or here. So you need to understand that here, where is the mean position, the kinetic energy is maximum and the potential energy is zero with respect to the movement, right? When it goes from here to here, the kinetic energy becomes zero and the potential energy becomes maximum. And on the other side, it is also the same case. Here, the kinetic energy is zero and potential energy is maximum. So let's look at what happens. When you start from this position right here, so at this point, the displacement is basically zero. So when you go this way, say you go this way, you go to a positive displacement, right? When you go to a positive displacement, the velocity becomes zero. So if you look at it, this is the mean position, and when you go to the maximum displacement, the velocity is right here, it is zero. Do you guys understand what I'm saying?
Not really, sir.
Check this out. If I go from zero displacement, which is this point, right? This point, to a maximum displacement, which is x naught here. So I would go like this, right?
Sir, I'm unable to see your cursor.
My cursor. You can see my writing? Oh.
Now I can, yes.
Okay. So what I'm saying is, let me highlight this. This point, do you see this point?
Yes.
This is this point where displacement is zero, right? Let me say this point is A, right? So this is A. When I go from A to B, I get to this point. Do you agree?
Yes.
Which means that you have reached x naught, and that is the maximum position where the pendulum can go. If you go here, which means that the kinetic energy is going to be zero. Kinetic energy zero means velocity is going to be zero. You see here? At the same point.
Right.
Now, when it comes back, so basically, you see it loses potential energy and kinetic energy is maximum. So when it comes back to this position, again where displacement was zero, you see that the velocity was maximum. So that's V naught. Is it clear?
It is, sir.
When it goes to the other end, like you go from here to this place, which is negative displacement, so at this point kinetic energy is zero again. So you are at negative displacement right here, but then the velocity is zero. Is it clear? So what we learned from this is basically between these two graphs there is a 90-degree phase difference, which means that when one is like maximum, the other is zero, and when the other is zero, the one is maximum. Is it clear?
Yes, sir.
Now check out the acceleration thing. When the displacement is right here positive, so acceleration will act towards the mean position in the negative direction. So you see, and the maximum value. So when displacement was zero, acceleration was also zero. When the displacement was positive and maximum, the acceleration was negative and maximum. Do you guys understand this? Check this out.
Yes.
When it was zero, the acceleration was zero. When the displacement was negative maximum, acceleration was positive maximum. And when it was zero, it was zero. So basically, what we learned from this is that between these two graphs, like displacement and acceleration, this graph and this graph, they have 180-degree phase difference. So they're always the same magnitude, but always in the opposite direction. Okay.
Sir, if we relate the second and the third graph, when we have maximum velocity, how can the acceleration be zero?
Very good question. That's what I'm expecting. Now, check this out. You see, the thing is, let's take an example of a rubber band, right? So if you stretch a rubber band looked like this when it was normally there, right? When you stretch the rubber band like maximum, right? Do you feel the force there?
Yeah.
Which means if you feel the force, it means there has to be, the rubber band wants to come back to its original shape, so acceleration has to be there, although the velocity is zero. Do you guys understand? Now, when it is coming back, right? It's coming back. So the acceleration basically reduces because the force is gone. So it reduces to zero, and now it goes to, at this point, temporarily it is going at constant velocity. Here the velocity is constant and maximum. Do you understand?
Yeah, okay.
So there could be velocity which is constant, acceleration zero. That is why you see when velocity is maximum, the acceleration is zero. Understood?
Yes, sir.
Excellent, right? So now we learn this. Acha, now I just want to, basically the last thing we're going to do is we're going to do a question, okay? And I just want to show you, if they give you another equation, how to deal with that, right? So let's do a question and then we're going to continue it tomorrow. So it says that an object is released from its lowest point, okay, in a vertical spring loaded pendulum system. So basically what it means is that you're like going up and down like this, okay? Now, they say the max displacement of object is 3.5 centimeter on either side, okay, of equilibrium. Okay. Now it says assuming 3 oscillations are covered in 2 seconds. So first of all, they say they have given you a graph. Let me show you a graph, and then from the graph you're going to learn what basically they mean. So the graph is like this. Okay, the graph looks like this, and this is 3, they have given plus 3.5, this is negative 3.5, and this is x in meters, and that's time. Okay, so this graph is given, and now they say derive an expression for displacement. Okay, now by just looking at the graph, who can tell me which kind of graph is this? Is this a sine graph? Is it a cos graph? Is it a negative sine or negative cos? Who's going to tell me? Any idea?
A negative cos.
That's
Is it
correct.
cos?
That's correct. Very good. This is a negative cos theta graph. How do I know this, or how do you know this? Because you see it starts from the negative value, so there has to be negative sign here, and a cos graph always, when it is 0, the cos graph is maximum. It starts from the maximum. Everybody understands this? So this means that I got to derive an expression like this. Now check this out, my friends. So what I'm saying is, then I could write x equals to x naught, and here I have to put a negative sign because it is a negative cos, and cos of omega t. Do you guys understand this?
Yes, sir.
Right? Now this is not the end of the question, because they will also want you to put the values in. So how do you put the values in? Let's check it out. This was in centimeters. Okay, now so omega, which we know is equivalent to 2 pi upon t from the very first chapter. So we should remember that here they say that basically 3 oscillations are covered in 2 seconds. So we can say, okay, 3 oscillations in 2 seconds. Then how many oscillations? So what about 1 oscillation in how many seconds? So we can cross multiply this. So 1 oscillation will be equivalent to, what do you say, 2 by 3. Is it clear? So that's the time period. Everybody understands this? Again, look at this. What I did was, if 3 oscillations are done in 2 seconds, then 1 oscillation is done in how many seconds? So we're going to cross multiply this. So this will be 3x equals to 2. So x will be 2 by 3 seconds. So that is the time period. Everybody understands this?
Yes, sir.
Now I'm going to put this here. So can I write it as 2 pi over 2 by 3. So omega will be equal to, basically 2 and 2 will cancel out. So it will be 3 pi radians per second. So I got the omega, and now I can fill in the values. So x equals to minus x naught cos of, x naught की भी तो value है ना, it's 3.5 times 10 raised to minus 2, because this was in centimeters, I wanted it to be in meters, cos of 3 pi and t, and this is the answer to this question. Is it clear, everybody?
Sir, the equation they use, it depends on the function, right?
Of course, that's why there is no fixed equation. The only fixed equation in this whole chapter is a equals to minus omega square x. Is it clear?
So if it would have been sine, so it would be x equal to x naught sine omega.
Yes,
Right.
and let's suppose if they had given you something like this, right? They're like, okay, they've given you something like this, okay? And there's x and t. So this would be x equals to minus x naught sine of omega t. Do you understand? Because this is a minus sign function. So basically you need to look at what the function is, and that's why I taught you the math thing. Otherwise I don't want to teach you extra things, okay? Do you understand now? Okay. Now, last question here, and then we're gonna close the class, okay? So they say in the same question, sketch, and this will be like every time you do questions from the past papers, they will, ask you this, and this is very important. They say sketch the acceleration time graph. Now you see they want acceleration time graph, right? So for that I should remember that how do I find the acceleration through displacement? Can I do that? Do you guys know any equation that relates acceleration and displacement? Go on. Nobody knows? Too bad. acceleration is minus omega square
minus
x,
omega square
right?
x.
So if I want to find the maximum acceleration, I want to put the maximum displacement, right? I have omega already, which is 3 pi whole square, and displacement is 3.5 times 10 raised to minus 2. Okay, like that. So first I want to find the value. I'll do that using minus 3 pi. Always use the pi from the calculator, never use the other one. So I'm getting acceleration to be minus 3.11 meters per second square. That's enough for me. And now I want to know what kind of equation. If this is the graph, can somebody tell me what will be the function of acceleration? Just the function, like cos theta minus cos, whatever. Who's going to tell me? So for acceleration, it will be the similar graph but a flipped one, which means when displacement is negative, the acceleration is positive. You guys remember that, right? So what I'm going to do is, let me copy this, right? Because then it saves a lot of time. Erase stuff here. So right here, okay, here, and I'm going to erase all this. Oh no, not this, and this. Okay, and I want acceleration in meters per second square and time now, seconds. So if you look at the graph, right, it will be something like this. Do you guys understand? And this value will be 3.11 and this value will be minus 3.11. Just look at the two graphs. Do you see the difference?
So we have to give the exact values or just
Exact values. That's why I had to find the maximum acceleration value. Do you understand? So not only you should remember that basically it is 180 degrees of the displacement graph, but also you need to remember to find the value of acceleration through the formula a equals to minus omega square x. Is it clear? Other than that, it's fine. You could also derivate the equation, but that would take too much time because you have to derivate displacement to velocity and then velocity to acceleration, so it will take a lot of time and it will give you the same answer, so we don't really need to do it. Is it clear? All right.
Yes.
Gatika, Suman, Soha, Fatima, and where is Rafe? Okay, Rafe, Nashima. Rafe is not here, Nashima. Okay, so I will see you tomorrow then, same time. I will post the recording. You can actually watch it if you want to. Bye. Have a nice day.
I said
Bye.
Bye, sir.
Bye. Oh, Fatma. Oh no. All right. Bye.
Sir.